All right, first I also want to thank ICTAS for funding. This is a pretty multidisciplinary project where we're bringing a lot of different ideas and different faculty, so it's a great funding mechanism for us. So what we wanted to do in this project is, first let me introduce the team. My team involves myself, Tim Long, having a great chemist who's wonderful. Chris Rylander is helping us with device design delivery nanoparticles. John Robertson, who provides cancer expertise, and Ji Wang was helping us with imaging. So our overall goal is to really find ways for which we can really improve the selectivity and lower toxicity for different types of treatments. There's a variety of different cancer treatments out there, but many of them have differing challenges. So the ultimate goal is to have this specific treatment that also might be specialized for the patient. So our overarching question was really, could we use carbon nanohorns as a mechanism to be a theranostic platform? By theranostic, I mean treatment as well as imaging and detection. So first, let me say a little bit about carbon nanohorns. This is one right here. It's, for the most part, still a very, very highly under-investigated nanoparticle for therapy and imaging. And it has some unique advantages. The ways in which it is actually produced is by laser vaporization of graphite. There's no metal catalyst, so the potential toxicity as compared to other carbon-based nanostructures is much lower. A really nice aspect of this carbon nanohorn as well is it has enormous surface area. So compared to gold nanoshells, what we've calculated with our collaborators at Dave Geohagen there at Oak Ridge National Labs is 50 times the surface area of gold nanoshells, and for single-walled nanotubes, at least 10 times the surface area. So, and that is because we have interior and exterior pores, which are not shown here, which provide a really nice mechanism for loading of drugs and imaging agents. So what we wanted to do in this project, our two goals were to develop a theranostic platform for which we could actually have both imaging as well as treatment, and to see how could we evaluate the ability of this particular platform both in vitro and in vivo. So I'll just talk briefly. Here's our nanohorn. What we're looking at in our particular case for the theranostic platform is we wanted to introduce quantum dots, and the purpose of this is that so that we could actually track the nanohorn in terms of cellular uptake. We would also do this in vivo. We have some experience with Harry Dorn's lab where we actually put buckyballs containing gadolinium inside, which was very nice for MRI imaging. But we wanted to look at the quantum dot. And we actually spent a lot of time trying to attach the quantum dots in a very stable form to the nanohorns, more time than we ever anticipated. We have a paper right now, a joint paper in the Journal of Nanoparticle Research with one particular method. But more recently, we've been working with Tim's group, where he made us a large number of different types of copolymers, and that actually contain histamine and PEG. And so the nice part is that we can have very, very nice, strong bonding between the zinc and the imidazole groups here. And so in our initial evaluation of this, we found this to be a very, very stable way of doing this. We're still kind of refining the method, but this has a lot of promise. We're going to use the same block copolymers to actually attach folate, and as well, we're looking at different ways to actually load the drug within the single tubes of the nanohorn, as well as integrating that within the polymer. So not only is it to develop this platform, but we also want to use it as a combinatorial mechanism with laser-assisted treatment. So we're working with Chris Rylander's lab. He has a really nice fiber optic device, which we'll talk more about, where we have looked at delivering the nanoparticles into bladder tissue in particular, and then following up with laser feeding. I'll show some of those results. This actually shows a bladder that's inflated. We have actually introduced the nanoparticles, that's them right there, and followed by exciting those nanoparticles within the bladder to try to have a very localized treatment. Bladder cancer is nice because we can actually access it with fiber optics, get very close to the tumors, which can be treated surgically, but typically these tumors embed within the wall, and it's very difficult to actually effectively treat these without we've done some initial studies here. All of it is about clinical translation. We actually have a team here in VetMed that's helping us to evaluate different treatments with the nanoparticles and laser therapy in some pigs, and we've got some very nice initial results with that. So just to talk a little bit about the deliverables, sorry there's a lot on here, I just wanted to talk a little bit about the highlights. Some things that we've been doing is we've looked at a variety of different types of polymers, is actually characterizing these particular polymers and our ability to image. So what you kind of see up here, first we looked at the optical spectrum. When we have nanoparticles or nanohorns, quantum dots and their conjugate, and we see that there are characteristics that our conjugate has of both quantum dots and the nanohorn. We have this characteristic absorption wavelengths less than 500 nanometers. We also look at our fluorescence here. Our conjugate kind of has a shift in fluorescence as compared to the quantum dots, so that's looking very promising. We've done some dynamic light scattering to kind of confirm our particle size. And typically right now our aggregate particle size is about 100 nanometers, and it confirms, I'll show that that's still very minimal in cellular uptake. What I show here is not only is us evaluating the particle important, we want to really understand the thermal dosimetry when we actually introduce these particles and heat with our laser. So we got a little crafty, wanted to see if we could actually introduce the particles. It's a little bit difficult to see, but there's a BT right there. Introduce the particles, excite those with the laser, and actually do some thermal camera imaging to be able to see the light distribution, in our case looking at the temperature elevation within the tissue. We don't want to just see that, we also want to be able to quantify it. So here's us again showing introducing the nanoparticles here and actually recording that temperature elevation, which we found after picking appropriate laser parameters and nanoparticle properties that we can get very significant temperature elevations that are conducive to treatment. So we spent quite a bit of time actually trying to understand what is the role of increasing the nanoparticle concentration, how can we both optimize heating as well as minimize toxicity. So this graph here actually shows our temperature elevation as a function of the nanoparticle concentration. One other area that we're looking at is how do we actually evaluate the therapy success quantitatively. So a big challenge is how do you actually quantify the treatment margins? As engineers, we always like to quantify everything. So one of my students has been spending a lot of time trying to develop image processing algorithms to be able to say that this is the volume of the treated region, both in 2D and our 3D representative phantoms as well as in vivo. So what we've done is we take our typical thermal camera images, we then, if you'll see the red and the blue, we can stain the cells. I'm just going to illustrate it simply with the 2D analysis, but we can stain the cells, so look at live and dead cells, correlate that with our temperature overlaid on our staining. So these are just kind of the thermal isoforms here of our temperature overlaid on our cell viability. You say, well, why is that important? The important data that we can get out of here is actually, we can now understand, this is just one example here for a 2D system, we've got temperature as a function of distance, 0 being where we laser irradiate our sample, and then viability. So what we can do here is kind of get an idea is what is that treatment region of our particular sample. So at 0 where the laser radiation occurs, you can imagine there's very high maximum temperature elevation, very low cell viability. But as we start to move away from that laser source, we can start to see how temperatures dissipate and viability becomes higher. So we really want to see what is that region where we start to get maybe a transition zone where tumor cells can recur, and try to use that as information to be able to improve our treatments. So we're doing that in vitro. We're also doing it in 3D phantoms, where we can also map temperature. We can also map viable and non-viable cells and quantify that. And we're also working on metrics to be able to assess the photothermal therapy in vivo as well. So that's an ongoing effort. So as we start to improve our nanoparticles, integrate those with laser therapy, we have nice analysis tools to look at that. And just finally, we're also very interested in the transport of the particles. We looked at a variety of different cancer cell lines, bladder, we have some brain, and we also have some breast cancer cells. And what you're seeing here is a little bit difficult to see. The green is staining of F actin, so you can see the morphology of the cells. Blue is the nuclei, and red are the quantum dots. So these are showing 24 hours. You can see the quantum dots are localizing in the cytoplasm, and we also see them close to the nucleus as well. So we think with their size, they're readily uptaken, could serve as a nice drug delivery platform, and we use flow cytometry to quantify the kinetics of varying types of cell lines. We're also trying to, in the future, start to look at transport within our 3D systems. We have tumor systems that actually have a vasculature. They have a nice surrounding tumor system for which we can start to really understand in a 3D controlled system what is the transport of the nanoparticles, start to evaluate targeting to therapeutic success. And we can also model how those tumors progress over time as they start to grow, become metastatic, what's changing our ability to treat these. So we do have a number of grants in review with NIH. I plan to submit an NIH R01 in June as well. So I know it's a lot of material, but we have a lot of exciting things going on with this multidisciplinary project, and I'm really excited to have such a great team to work with and have the funding to continue to move this forward. Thank you very much.
Is Chris about the fiber optic microneedle?
I do want to thank ICTAS for the generous support of this research on fiber optic microneedle device for therapeutic cancer vaccine delivery. My collaborator on this project is Kumran Sabai in veterinary medicine. And we had a postdoc, Charles Smith, who is biomedical engineering. Now he's transitioned off the project. He was more the engineer, helping us get the device ready to go for this application. And now Dr. Sabai has a new postdoc who just started yesterday. And to give you an overview for the significance of this project, it is that therapeutic vaccines for non-infectious settings such as cancer really do not exist. And part of the reason is that it is difficult to achieve a cellular immunity to that cancer. And what we're trying to do in this setting is target epidermal Langerhans cells, which subside in the epidermis, the upper layer of the skin, which are known to, when stimulated, promote that cellular immunity response and therefore enable cancer vaccines. Unlike the current intramuscular